Bismillahirrahmanirrahim. Today is our third lecture of this automotive technology series course. Before going to the chapter, the topic is drive axle shaft, joints and differential. Before starting this topic, one thing which was missed in our last lecture, the conventional transmission, regarding the transmission oil. We are using gearbox, the transmission. A lot of mechanical components are moving there. Gears are continuously mesh and moving at a high speed. So we need to have some lubrication there. We need to have some reduce friction there. We need to remove some heat which is generated there. So we require some fluid, that is the transmission oil, which we used in the transmission for the lubrication of the mechanical parts, the gear, the shafts, the linkages, and to reduce the friction between the metal parts which are there. Now, coming towards our today's lecture, that is drive axle shaft, joints and differential. This lecture is in two parts. In first part, we will cover the propeller shaft, joints, and in next part, we will study the axle shafts and differential. So the main slides which we are discussing the powertrain or power flow in a conventional rear wheel driven vehicle. We have studied these topics: engine, power develop in our IC engine course. Then we studied the flywheel and the clutch in our first lecture. Then the gearbox in second lecture. Now the third lecture is propeller shaft, CV joints or joints and differential box. So this is our today's topic. First of all, now what is drive shaft or propeller shaft? Drive shaft is a term used by the Society of Automotive Engineers to describe the shaft between the transmission and the rear axle assembly on a rear wheel driven vehicle. General Motors and some other manufacturers, OEMs, use the terms propeller shaft or prop shaft to describe the same part. A typical drive shaft or propeller shaft is a hollow steel tube. A spline end yoke is welded onto one end that slips over the splines of the output shaft of the transmission. Let's see how this happens. Basically, this is the typical rear wheel driven powertrain arrangement. The engine is mounted longitudinal lengthwise. So this is your engine. Here you have the flywheel and the clutch. Then this portion is your transmission. Here it is the propeller shaft, the drive shaft or the propeller shaft. These are the U-joints. There are two U-joints, one on both ends, one on front end and one on the rear end. And this propeller shaft is joined at the end. One end at the transmission, second end is with the differential. And from that differential, the power goes to the axle shaft and then to the wheels. So this is the propeller shaft which we are, or prop shaft or the drive shaft which we are talking about. Now, the splines which we talked about in the previous slide, this is your transmission with this output shaft or splines on the outer side, and this is the slip yoke having a splines on the inner side. And this is your front U-joint. Then we have this propeller shaft or drive shaft. This is rear U-joint and it is connected with your differential. Okay. Drive shaft or propeller shaft construction. Most drive shafts are constructed of hollow steel tubing in which forces are transmitted through the surface. The surface is therefore in tension and cracks can develop on the outer side surface of the drive shaft due to metal fatigue. If dented, can collapse. So I read again. Most drive shafts are constructed of hollow steel tubing in which forces are transmitted through the surface. The surface is therefore in tension and cracks can develop on the outside surface of the drive shaft due to metal fatigue. If dented, can collapse. Most rear-wheel drive cars and light trucks use a 1 or 2 piece drive shaft, depending upon the length arrangement, how much far is the transmission from your differential. So most rear-wheel drive cars and light trucks use 1 or 2 piece drive shaft. A steel tube drive shaft has a maximum length of about 65 inches or 165 centimeter. So a propeller shaft or drive shaft of hollow steel tubing can have a maximum length of 65 inches. Beyond this critical length, a center support bearing must be used, also called steady bearing or hanger bearing. Why this length is critical if we increase this length, because it is moving at a high RPM, so it will have a buckling effect. So beyond this critical length, a center support bearing must be used, also called a steady bearing or hanger bearing. So if we want to increase this length, then we have to use a steady bearing or a hanger bearing. Some manufacturer uses aluminum drive shaft. Previously that was hollow steel tubing. Now some manufacturers, or in the latest manufacturers, the latest trend is aluminum drive shafts. These can be as long as 90 inches. So instead of 65 inches, they are 90 inches long, 230 centimeter, with no problem to eliminate the need and expense of a center support bearing, because aluminum alloy shafts are lighter in weight, so with no problem to eliminate the need and expense of a center support bearing. Again, another latest trend, composite material. Carbon fiber plastic drive shafts are also used in some vehicle. So this is another trend, that with the help of composite material, a carbon fiber plastic drive shafts are also used in some vehicles. To dampen drive shaft noise, because it is moving, it is rotating at a high RPM. So to dampen the drive shaft noise, it is common to line the inside of a hollow drive shaft with cardboard or rubber. So to dampen the noise, we use the inside of the hollow drive shaft with cardboard or rubber. Design drive shaft design. Same diagram which we have seen: engine, then we have a transmission, then this is the propeller shaft with two U-joints on both ends, then differential, and the axle shaft, differential going to the right and left axle shaft, and then to the wheel. Now, if we have this type of front wheel driven vehicle, where the typical front wheel driven powertrain arrangement, the engine is usually mounted transversely. Previously, it was longitudinal arrangement in a rear wheel drive vehicle. Now, if we have a front drive vehicle, it is transversely mounted. So this is your engine, and this assembly is your transaxle. Transaxle, as I have already explained in the previous lecture, is when we call it transaxle assembly, then it is a combination of your clutch assembly. Clutch assembly means your flywheel and a clutch, the gearbox, the transmission, and the final drive unit, which is also known as differential. And from that differential, we are having these inner plunger type CV joints. The power is coming to these, and then we have this right side, or it may be left side drive axle shaft, or right or left drive axle, driver's side drive axle shaft. Then we have outer CV joints on the both end, and then it is attached with the wheel. Now, talking about the U-joints design and operation. U-joints is universal joints, are also used at both ends of the drive shaft. U-joints allows the wheel and the rear axle to move up and down, remain flexible, and still transfer torque to the drive wheels. The function of the U-joints is it allows the wheels and the rear axle to move up and down, remain flexible, and still transfer torque to the drive wheels. A simple universal joint can be made from two Y-shaped yokes connected by a cross member called a cross or spider, like this. This is a yoke, one yoke and second yoke. This is a cross member. Cross member, we have a trunnion at the end. A simple universal joint can be made from two Y-shaped yoke connected by a cross member called a cross or a spider. The forearms of the cross are called trunnions. These forearms are called the trunnions. For a line drawing of a simple U-joint with all parts name identified, torque from the engine is transferred through the U-joint, then to the propeller shaft. So these are the Y yokes, two yokes, and this cross member is called the spider, and where it is attached with the U yokes, that point is known as the trunnions. U-joints design and operation. The engine drives the U-joint at a constant speed, but the output speed of the U-joint changes because of the angle of the joint. If input is coming from this side, but output is coming from this side. So there is an angle here. The engine drives the U-joint at a constant speed, but the output speed of the U-joint changes because of the angle of the joint. The speed changes twice per revolution. So in 360-degree, the speed changes twice. The greater the angle, the greater the change in the speed velocity is. We will see. If only one U-joint were used in a drive line, this change in speed of a driven side output end would generate vibration in the drive line. To help reduce vibration, another U-joint is used at the other end of the drive shaft. So if we use only one type of a U-joint, it will create a lot of vibration, and to reduce or minimize those vibration, and we use another U-joint at the other end of the drive shaft. If the angle of both joints are nearly equal, the acceleration and deceleration of one joint is offset by the alternate deceleration and acceleration of the second joint. Ideally speaking, they should be in the same plane, but as far as the construction and the space limitation, there is some angle. So acceleration and deceleration of one joint is offset by the alternate deceleration and acceleration of the second joint. It is very important that both U-joints operate at about same angle to prevent excessive drive line vibration. So designer has to take into this consideration that they both joints, the front end U-joint and the rear end U-joint, should operate at the same angle to prevent this excessive drive line vibration. Now, first let's see how the speed difference on the output of a typical U-joint varies with the speed and angle of the U-joint. At the bottom of the chart, this one, we are talking about now this portion. From here to here, this is one complete revolution, 360-degree. Okay. The input shaft is moving at 1000 RPM and the output yoke having an angle of 10-degree. Output at 10 joint angles. So the fluctuation or the variation is from 900 to 1100 RPM. At the bottom of the chart, the input speed is a constant 1000 RPM, while the output speed varies from 900 RPM to 1100 RPM when the angle difference in the joint is only 10-degree. So input shaft and output shaft. Input shaft is moving at a constant speed at 1000 RPM. Output shaft having an angle of 10-degree First, it will be accelerate till 90 degree, then deaccelerate to 180 degree, then accelerate, then deaccelerate. So twice it changed the speed. Now, at the top part of the chart, the input speed is constant at 1000 RPM. So same input speed is at 1000 RPM. Yet the output speed varies from 700 to 1200 RPM when the angle difference in the joint is changed to 30 degree. So here in this chart, in this portion, your angle variation is of 10 degree. So less of a fluctuation from 900 to 1100. Same input speed, but the angle is changed of the output shaft that output joint, that is 30 degree. So fluctuation variation is from 700 to 1300 RPM. Increasing, decreasing, increasing, decreasing. So twice it's changing in one revolution. So this how your universal joint varies the speed if there is some angle. Now, constant velocity joint or CV joint, purpose and function. Constant velocity joints, commonly called CV joints, are designed to rotate without changing speed. So CV joints are different than universal joints. In universal joints, the angles matter. Angles matter, the speeds change, the velocity change. But in CV joints, it rotate without changing the speed. So let's see. Regular U joints are usually designed to work up to 12 degree of angularity. Regular U joints are usually designed to work up to 12 degrees of angularity. If two Cardan style U joints are joined together, the angle at which this double Cardan joint can function is about 18 to 20 degrees. Let's see. This, if you have a double Cardan U joint, one U joint is here and second is here, but both are combined together, then we call it as a double Cardan U joint. So angularity is changed from 12 to 18 to 20 degree with double Cardan joint. Double Cardan U joint were first used on a large rear wheel drive vehicles to help reduce driveline induced vibration, especially when the rear of the vehicle was fully loaded and drive shaft angles were at their greatest. So previously it was single Cardan U joint, but we use double Cardan U joint in a large rear wheel drive vehicles to help reduce driveline induced vibration, especially when the rear of the vehicle was fully loaded and drive shaft angles were at the greatest. Now, constant velocity joint, CV joints, allows a drive shaft to transmit power through a variable angle at a constant rotational speed without an appreciable increase in the friction or a play. A constant velocity joints allows a drive shaft to transmit power through a variable angle at a constant rotational speed without an appreciable increase in the friction play like this. They are mainly used in front-wheel drive vehicles and many modern rear-wheel drive cars with independent rear suspension typically use CV joints at the end of the rear axle half shaft and increasingly use them on the propeller shaft. So they are mainly used in front-wheel driven vehicles and many modern rear-wheel driven cars with independent rear suspension typically use CV joints at the end of the rear axle half shaft and increasingly use them on the propeller shaft. As long as a U joint, either single or double Cardan, operates in a straight line, the driven shaft will rotate at the same constant speed velocity as the driving shaft. As the angle increases, the driven shaft speed or velocity varies during each revolution. This produces pulsation and a noticeable vibration or surge. The higher the shaft speed, the greater the angle of the joint, the greater the pulsation are. So CV joints are used to minimize these things. Now let's see. From here to here, we have a one revolution of a propeller shaft. This is your driving shaft at a fixed angle. Now driven shaft is at 30-degree angle. So speeds of a driven shaft for a driving shaft of 1000 RPM. So this is the input shaft, the driving shaft, which is moving at 1000 RPM. Now with the driven shaft, its speed varies from 850 to 1150. First it will accelerate, then deceleration, next 90-degree, then acceleration, next 90-degree, then deceleration, next 90-degree. Conventional universal joint showing fluctuation. Conventional universal joint degree of rotation. Constant velocity universal joint no fluctuation. Shaft angles in degree. If we have a shaft angle in degrees 8, 10, 15, 20, 25, 30, 40. Maximum variation in driven shaft speed percent is like with respect to these degree, it is like this. Now types of CV joints. There are four types of CV joints. First one is Zappa CV joints. Then we have Bandex Vias, this type of. Then we have Tracta joint, this type. Then we have a double cross and roller. So these are the four types of CV joints which are used, but the most commonly used is the Zappa type CV joint. The Zappa type CV joint is most commonly used as an outer joint on most front wheel drive vehicles. Like this. A Zappa fixed joint on a front wheel drive vehicle. This type of CV joint is commonly used at the wheel side of the drive axle shaft on front wheel driven vehicle. The joint can operate at high angles to compensate for suspension travel and steering angle changes. So, most commonly used as an outer joint on most front wheel drive vehicle. Outer CV joints are called fixed joints. There are two types of joint, inner CV joints and outer CV joints. The outer CV joints are called fixed joints. The outer joints are also attached to the front wheel. They are more likely to suffer from road hazards that often can cut through the protective outer flexible boot, the rubber boot or the rubber cap which are placed to cover the joint. They are mostly in cut by this road hazards. The outer joint must do the following. Allow up to 40-degree of or more movement to allow the front wheels to turn. So the outer CV joint must do the following. Allows up to 40 degrees or more of movement to allow the front wheels to turn. Allow the front wheels to move up and down through normal suspension travel in order to provide a smooth ride over rough surfaces. Be able to transmit engine torque to drive the front wheels. So three function. Allow up to 40-degree of turn. So if your wheels are straight, they can move 40-degree right or left. Okay. In total, 20-degree on either side. Allow the front wheel to move up and down. So this was in lateral and this was in up and down movement through the normal suspension travel. And third function is to transmit the torque to drive the front wheels. So this is the simple construction of a Zappa joint. We have this boot which cover this all the assembly. This is the inner race. Then we have a cage, then ball arrangement, the clamp, and fixed joint housing. Zappa joint transfer torque through 6 balls, round balls that are held in position midway between the two shafts. As we have seen that clip, The Zappa joint transfers torque through 6 round balls that are held in position midway between the two shafts. This design causes the angle between the shaft to be equally split regardless of the angle. So these are the 6 balls which splits the angle equally. This design causes the angle between the shaft to be equally split regardless of the angle. Because the angle is always split equally, torque is transferred equally without the change in the speed velocity that occurs in Cardan-style U-joints. This style of joints results in a constant velocity between driving and driven shaft. So because of this arrangement, we can transfer the torque without reducing or increasing in a revolution. Because the angle is always splitting equally, torque is transferred equally without the change in speed velocity that occurs in Cardan-style U-joint. This style of joint results in a constant velocity between driving and driven shaft. It can also function at angles greater than simple U-joint that can up to 40 degree. If we have a simple U-joint, we know that it can goes up to 12 degree. If we have a 2 U-joints or double Cardan U-joints, then the angle which can we achieve 12, 18 to 20 degree. But with the help of this CV joint, it can function up to 40 degree. So a constant velocity CV joint can operate at high angles without a change in velocity speed because the joint design results in equal angles between input and output. So this is the axis, and this input axis and this output axis, the equal angle is there. So another illustrated view of this Zappa joint. Ball arrangement, inner cage, then outer race, and then this is the assembly part. Then next is the bandage vise. It also contains these balls, but we have this arrangement. Axle, universal joint knuckle, groove pin. Then we have drill ball pin and universal ball joints, spline to wheel hub, and axle shaft. Then we have a tractor joint, CV joint. We have this axle shaft, both at the end, then bushing and universal joint in between. Universal joint outer portion, universal joint inner portion, and then we have this axle. So this is the arrangement working of a CV joint of Zappa. Now, a tripod fixed joint. This type of joint is found on some Japanese vehicle. If the joint rear out, it is to be replaced with an entire drive axle shaft assembly. So we have to replace all the drive axle shaft assembly. Here in your vehicle, this is the CV joint which we are talking about. This is the rubber cap or rubber protection on the joint. Now, few words regarding the inner CV joints. First, we have studied the outer CV joints. There were 4 types of outer CV joints, and those were Zappa, Bendix Vise, Tractor, and double cross and roller bearing. Now, inner CV joints. Inner CV joints attach the output of the transaxle to the drive axle shaft. So the inner CV joints attach the outer output of the transaxle to the drive axle shaft Inner CV joints are therefore inboard or towards the center of the vehicle. The fixed outer joint, this is the CV joint, is required to move in all directions because the wheel must turn for a steering as well as move up and down during suspension movement. The inner joint has to be able to not only move up and down but also plunge in and out as the suspension moves ups and down. So your wheel is here, it is going up and down, so this inner CV joint has to move up and down, and it should be moving in this direction also. Inner CV joints are therefore inboard or towards the center of the vehicle. Inner CV joints have to be able to perform two very important movements. Allow the drive axle shaft to move up and down as the wheels travels over bumps. So first function is, or the very more important moment is, allow the drive axle shaft to move up and down as the wheels travel over bumps. Allow the drive axle shaft to change length as required during vehicle suspension travel moment, means in and out. Allows the drive axle shaft to change length as required during vehicle suspension travel moment, lengthening and shortening as the vehicles move up and down, same as the slip yoke on a conventional rear wheel driven shaft. Inner CV joints are also called plunge joints. Inner CV joints are also called plunge joints. So this is the plunging which is going on here. So with this, we comes to the end of the first part of our chapter 3, that is up till drive axle. So thank you very much.